Where is the record button?
I recorded. I started recording.
Oh, you're the recording guy. Okay, perfect. So, can you also pin the camera?
I did.
Okay, then everything's ready. Okay, then welcome. So we have our new postdoc, Subhroneel.
Yeah,
correct. Perfect. So welcome to new therapy. So we'll be talking about cellular field strengths, and yeah, we're happy to have you. You can start.
okay,
The
thank
floor is
you.
yours. Okay.
Okay, so I guess the plan of this lecture series is quite open in terms of how many lectures and what to cover. So I leave it, a large part of it, up to you. Like you decide that what and how much you want to know about. So the main focus is cellular field strengths. This, of course, has a sort of long and interesting history, and we are not going to cover the whole historical part. We are going to focus on a very specific formalism, which is due to Ashoke Sen, and it's since been called as Sen's formalism. And that would be our main focus for this lecture series.
Is this Sen's paper you have written?
Yeah. So this, for this week's and next week's lecture, I think this archive paper by Sen in 2019 is the reference. I'm pretty sure I'm going to follow the conventions and notations of this paper. So just so that you can go back and read it and you will find synergy with whatever we are discussing here. And then in the next, if it is continued beyond 2 lectures, 3 and 4, there will be some other papers which we can discuss, including some of them. Okay. So another thing is that I actually had no idea what to expect from background wise. So because there are students and there are experts, so I have risked at the cost of boring the experts to make sure that the students can follow. So if you find that it's too slow or too boring, just egg me on, then I can speed up. And
I think we can speak that there's no chance of that.
Okay, so without further ado, let's start. So, given a manifold N, and suppose this has some dimension D, all of us know that how to sort of define P-forms. They typically belong to some vector space, which we denote by this. And in components, we would denote a P-form AP as a tensor with P indices after you have chosen some nice basis of x1, x2, or x0, x1, x2 up to x3 minus 1 or x1 of x, whatever, right? Now, these vector spaces, so if to basically find how many independent bases of this, it's basically choosing p number of these dx's out of the total d that you could have chosen, right? So the dimension of this vector space would be basically p choose d. Right? So, or sorry, it's the other way around. Yeah, the other way around. D choose p. And because this thing is equal to d choose d minus p, we immediately notice that the vector space of p forms and vector space of d minus p forms have the same dimensions.
Oh, I have some notation because I have read all this form from mathematicians, and they usually divide by
P factorial.
P factorial.
Yeah,
I am not
doing
Sen is not doing that.
Yeah. So if you want to convert it to the other notation, then you will just put a P factorial on it. In fact, typically I also divide by 1 over P factorial, but since I promised I'm going to follow that notation, let me stick to that. Right? So at this point, it's just an observation that these two vector spaces have the same dimensions, and it's a very natural question to ask that since these have the same dimensionality, can we have a one-to-one map between these two vector spaces? And it turns out that yes, there is a natural map once you provide metric G on this manifold. And that map is, as you all know, is provided by what is called the Hall star. This is a map from the space of P forms to the space of P minus P forms. And in components, it would look something like this. So let me what index should I use? Let's say row. Okay, so it's a big expression. Let's just break it up. So I'm going to take a star of a P form. So if I had just AP, that's the AP, right, in components. The star of this is going to be a D minus P form. So it's going to have D minus P free indices. Those free indices are this row 1, row 2, all the way up to row D minus P.
Yes, sir. The epsilon is the Levitsky tensor.
Yeah, I'm coming back. Epsilon is the Levitsky symbol. And that's why I'm going to divide it by this, right? Because it's the density, and this is the one that will make it a tensor. And in this lecture series, epsilons are always going to be the Levitsky symbols. I'm never going to use the Levitsky tensor. So I always, in non-flat backgrounds, I'm always going to write out explicit factors of square root g's and stuff like that.
So you also don't put any factorial.
Yeah, for the same reason that this a's are defined in this way, which means that when I'm going to sort of
You square this operation.
no, the square is still going to work out because the normalization of this epsilons is up to me, right? Whether in this normalization,
Are you taking some standard normalization?
yeah, I can put a sort of p factorial there.
Oh, okay. Because normally you would say that.
So
Yeah.
we would have plus minus 1.
Right, and then I can yeah, instead of that I can just put a p factorial there and get rid of the factor. So this is the sort of thing, but I mean this is very much convention dependent, like whether you have a constant factor or not. But the basic structure that I'm trying to tell you is that you have this epsilon symbol which immediately raises to d minus p indices, and then you need exactly that many factors of the metric to pull the indices down, and you need this guy to make this a tensor from a density, and then this is a tensor which has d minus p indices downstairs, so it transforms like a d minus p form, right? So that's the map essentially. Okay.
Okay, but I guess then you should have some free indices on the left hand side.
Yes, this one has the free indices is row 1. That's right. I mean, typically one would write this epsilons mu's downstairs to sort of, not write these factors of g's, but I wanted to write these factors of g's to emphasize the point that you really need the metric tensor. Otherwise, if you don't give me this metric tensor, then this Hodge dual is not defined. It's not something that I can come up from my hat, right? Okay, everyone has seen some form of this, right? You might not agree with the normalization or conventions, but everyone has seen some form of this. Okay, So that's the hot star. Now we are interested in trying to impose a condition.
I guess you could define a kind of hot star, but then you would have the indices up, so it would not be forms, but it would be like dual
Vectors.
I guess it's called polyvectors.
Yeah, polyvectors.
But you would still need a volume form.
Absolutely.
So you could go with a volume form.
Yeah. You would still, so, but that would be a map from the space of forms to the space of polyvectors.
Yeah, or densitized polyvectors.
Densitized polyvectors. Yeah. Right. But that's the best we can do if you don't give me a metric. Right. Whereas this one tells you that I'm really giving you a map between the, in fact, it's an isomorphism between the space of two forms. Right. Okay. So now what we are interested in is that we want to impose this condition on some P form such that when I put Hodge dual of this, I'm going to get that P form, same P form back. Okay. I'm and slowly, I'm going to sort of suppress the index notation and move over to the form notation because it's more cumbersome working with indices. Unless we're doing some explicit computation, then I will rightfully restore them. I'm hoping everyone is familiar with that. Now, of course, this is something that you can, first and foremost, this is not something that you can do for arbitrary P because this Hodge dual has a particular definition and it immediately tells us that you can only do this if P and D minus P are same, right? Because the Hodge dual of a P form is supposed to be a D minus P form. If I want it to be equal to a P form, then both should have the same rank. And this immediately tells us that this is possible only if the dimension is an even number, it's twice of P. And even for those dimensions, you can only impose it for the forms, which is precisely the half of the dimensions. Right? So from this point on, I'm going to set D equals to we are not even going to be able to impose this condition. So let's just forget about that possibility. But that's not all, because you see, this Hodge dual has this property, which precisely what Linus was saying, that if I act on this thing with twice, okay, I can tell you in my normalization, the Hodge square acting on some, let's call it n form. In fact, okay, this n and this n might be confusing, so let me call this is n form. So this Hodge star acting on an n form gives me a sign factor which is -1 raised to the power n times d minus n is the dimension which we are setting to 2n now. I will put it equals to 2n. This S is what is called the signature of the vector. Everyone is familiar with signature of the metric. Yeah. It's -1 if it's Lorentzian, it's +1 CPDN. So it's determinant of the metric divided by modulus of determinant of the metric. One way of thinking about this. So it will.
Is the number of negative? You mean the number of negative?
Yeah, you're thinking in terms of this difference in this eigenvalues. Like
Yeah, exactly. So,
yeah, that's another way of doing it. But I think.
But you really, when you say signature, don't you just need to how many negative eigenvalues?
Yeah, I mean, you can think like this, but here I think I'm suggesting an even simpler definition, which is this. This is what I mean. So I really care about whether the number of negatives and the positives, whether the difference is mod 2. So if it's basically
Right, yeah, so it is the -1 to the number of negative.
yes, in some sense, yes. Exactly that is, yeah. So in particular, in our convention, if it's a Lorentzian, then it's S is -1. If it's Euclidean, then it's +1. Right. And we are not going to work with space times with more than one time direction. So it's not worth.
And you're not doing West Coast, East Coast.
They definitely,
Mostly plus.
yeah, definitely. Okay. Okay, so we have this constraint as well. So if we want to entertain this possibility, first is that D has to be 2n, but then we can use this possibility, and then of course we have two cases depending upon whether S is +1 or -1. So if I pull this up, this one goes up automatically up.
Yeah.
No, you have to pull it cut off and then.
And you can still see that. Okay. So maybe let me just continue here. So the first case, we have a Lorentzian which means this S is -1. And then let's put n equals to 2n there. So the sign factor, it is, sorry, d equals to 2n there. It's 2n. And we want to impose it only on n, right? And this sign factor has to become precisely 1 for us to satisfy that star n equals to a. Right? This means this one gives n squared, and there's a negative positive here, which means I will have to have -1 to the power n squared to be a negative 1. That means n squared has to be odd, which means n has to be odd. So it means that in Lorentzian signature, you can successfully impose that condition that star of a form is equal to itself. Not only for d equals to 2n, but that n also has to be odd. So it has to be d equals to twice odd. Right? So let's put n equals to some 2k plus 1. And then that tells us that d equals to 4k plus 2. And p equals to 4k plus 1. We will have a condition like star a 4k plus 1 equals to star a 4k plus 1. Sorry, a 4k plus 1.
So it was D 4K plus 1, 2K plus 1.
Sorry, 2k plus 1, not 4. Here. Right?
What's the difference between K and E?
I'm just saying that because there I put it P, some arbitrary P form.
Oh,
I said that P has to be this 2k plus 1. D has to be
oh,
4k plus 2.
yeah, okay, that's the little difference.
Yeah. And then we have the second case, which is the Euclidean. So this is +1 here. The rest of the analysis is same, except that this -1 now becomes +1, which means that now you need to have -1 to the power n squared to be +1, which means that n squared has to be even, which means n is even, right? So everything just changes to this, that d has to be some 4k and p has to be some 2k. Now at this point, we have not done any physics at all. These are just statements about forms in a manifold with a metric. As simple as that. Okay. But I already want you to notice one thing, that there is a significant difference between where you can put this condition, which is, by the way, what is called the self-duality condition. The name is pretty self-explanatory. You can only put this condition in Euclidean case for 4 times integer dimensions on 2k forms, or 4k plus 2 dimensions for Lorentzian signature on 2k plus 1 forms. And this is a subtlety that we will come back to. It means that when we start doing physics with it, when you start doing quantum field theory with it, this is not something that you can just, in a cavalier, naive way, analytically continue weak rotate to an Euclidean space. This whole condition is going to break down. This is not something that we usually see in bosons, but this is something that we see for fermions. Right? Fermionic representation theory is quite different for Euclidean and Minkowski space. So in this sense, this is a boson which is kind of behaving like a fermion in some sense.
And by the way, anti-self-duality would be the same.
I was coming to. Yeah. So, and all of this argument you can see. Okay, maybe I don't have to raise it. All of this argument that we have argued, all of it goes through if you want to impose something like star A equals to negative of. So think of it like a homework. If you just take this as a starting point instead of that, you see that none of the analysis changes. Everything goes through. Okay. So that condition is called a self-dual condition. This condition is called an anti-self-dual condition. And everything that we are going to say in this lecture, I'm going to talk about self-dual, but they hold equally true for anti-self-dual cases. The only reason I'm going to talk about self-dual is because I have to write one minus sign less and speak one word less. That's no other reason. And it's purely a matter of convention, which one you want to work with, and which one you want to call anti, and which one you want to call. Okay, so all of this is pure kinematics, so to speak. This is just purely the setup, the mathematical setup. There is so far no physics in it. So now let's start putting physics in it. But if there are any other questions about this very basic setup, which I'm sure all of you are familiar with, but it might be a good point to ask. Okay. Okay, so let's start putting physics in it, and let's look at an example first. And of course, we are interested in Lorentzian signature. So this is the case which we are going to focus on. So what's the lowest dimension in which you can have a self-dual form with? Well, put k equals to 0. So that's it equals to 2. Or to emphasize that is Lorentzian, let's write it as is equals to 1 plus 1. And you have a one form, some v, which is equal to star v. Now, typically, for any 4k plus 2, this 2k plus 1 forms are usually thought of as some kind of field strength like variables. So you typically want to think of this v's as exterior derivative of some potential. Okay? Typically, that's what it is done. So, of course, in 1 plus 1, the field strength name doesn't really make sense because the potential is kind of like a scalar. So you really don't have a gauge symmetry, so to speak. You have a shift symmetry, that's it. It's not a local symmetry. But the name still sort of gets stuck. So let's say V is some D of phi. And this condition in components is essentially simply saying this. Right. Simple condition. And if you wanted to do anti-self-dual, you would have put a minus sign. That's all the. Now, if we work with a convention, let's say epsilon 0, 1 equals to 1, then you see that this simply tells us that del 0 phi is del 1 phi. And if you have flat space in our matrix convention, which is minus plus, this you can write as del phi without costing a sign. Bring it on this side, and this is essentially telling us that del minus phi is 0, where minus is x0 minus x1 by root 2. So just the self-duality condition, thinking of V as some derivative of a phi, tells us that it's basically giving us the equation, which is del minus phi equals to 0. There is
And the other equation, so that would just be with the other index, but that's probably the same.
Yeah, the other index are either going to give you identically 0 or it's the same index, same one. So for example, you might get del upper raised plus equals 0, but that is basically this raised, that's it. So you can check that there are no other non-trivial equations for this. So this is one equation. Let me say mark it. Let's call it equation 1. But there is something else that we can do here. We can, for example, in this equation, you can act with a del upper B. On the left hand side, you get box of phi. On the right hand side, you get identically 0. So you have this also true as a consequence of just the self-duality condition. Now, what the self-duality condition is essentially telling you is that typically, if you have such a plane wave equation, you would want to solve it in terms of phi would be solved in terms of something which is purely a function of the one dipole and then something which is purely a function of the other dipole. It's a massless boson propagating in 1 plus 1 dimensions, and I can find only these two combinations. But we also have another combination, which is del minus phi equals to 0. And that is essentially telling you that the only non-trivial solution is this. Okay. So it's basically a plane wave which is propagating only in one direction. So there's only one spatial direction. It's only propagating towards the right or towards the left, whatever is your naming convention. So which is the reason why these things were called chiral bosons. And strictly speaking, only 2D should be called chiral bosons, but somehow the name kind of got generalized. Like for higher dimensions, also people get confusing the term chiral bosons. Okay. Now this theory would look like to you like a simple theory which has dynamics, right? It's a free boson, free massless boson with an extra condition that del minus phi is equals to 0. And you would assume that this is something that I can derive from a Lagrangian. Because naively speaking, free massless bosons, I should know how to derive from a Lagrangian. And the naive Lagrangian that you would write down, del phi. Right. This is identically 0 because of this. Because if I have another del mu phi here, the del mu phi here, same argument. Right hand side, this is antisymmetric, this is symmetric, it's identically 0. So the naive Lagrangian that you would want to guess is something which is identically 0. On the other hand, you have a nice free equation of motion, which is perfectly Lorentz invariant. This is Lorentz invariant, right? And it gives you a dynamics which you know how to solve and so on and so forth. So this is the crux of the problem of self-dual things. And you can easily see that this story generalizes to higher dimensions. So now if I go back to, I call K, right?
Can I ask before you go to the next one?
Yes, sure.
Is there some non-trivial Lagrangian that will give you the equations?
Yes, that's the whole purpose of this.
Yes. So yeah, I guess you'll get to it later.
In fact, within 15 minutes, you will see one Lagrangian which does that.
Okay.
The whole point is that the simplest naive Lagrangian that you would guess would not do the job, do the trick.
Of course, you can always, whenever you have equations of motion, you can always take another answer. But that might have consequences.
Yeah. So again, just to generalize, so 4k plus 2 and we are looking at 2k plus 1 form field strength. So I have a f2k plus 1 and we are going to think of this as a field strength of a potential which is a 2k form, right? So the self-duality condition basically tells me that DC equals to stop DC. I'm going to stop writing the rank of the forms because it should be quite clear from the discussion what is going on. And now you see, if I act with a D on both sides, I get D squared DC equals to 0. Which if you take another star, this is precisely the box. It's equal to 0, so it's a massless 2k plus 1, 2k form.
Can I ask a question?
Sure.
So you need to have these self-dual forms to have chiral bosons. Does that mean for 4k dimensions, you will never have chiral bosons?
In Euclidean signature, you can.
But not for Lorentzian.
Okay, so there is one other thing that I should have mentioned, that's a valid point, is that I'm assuming that all of these forms are real.
Okay.
If you allow this to be complex, then you can impose something called imaginary self-duality, imaginary anti-self-duality. So you demand that star of A is not just A, but say I times A.
Okay.
Then that's a possibility of Lorentzian signature.
Okay.
For 4k dimensions to have. So in 4k you can have, in 4 dimensions for example, you can have imaginary self-dual or imaginary anti-self-dual.
Okay.
But you won't have self-dual or anti-self-dual unless you're working on Euclidean signature.
Okay.
But yeah, that's a valid point. I should have mentioned. Yeah, so this is the massless equation, right? And you would once again probably guess that, okay, why can't I derive it from Lagrangian, which is the usual one, DC with star DC. But that's problematic because star DC is exactly equals to DC, and wedge product of two odd forms, that's identically zero. Same odd form is identically zero. So this is the same problem in general dimensions. And this is a problem that is already at the level of free theory. There is not even an interaction present. So we couldn't even try to form an off-shell description at the level of free theory. But nonetheless, I want to emphasize this point that just the constraint itself seems to suggest that there is some sort of dynamics going on. So even though it might seem like, okay, it's just a kinematical condition, I'm just choosing to work with self-dual or anti-self-dual tensors, but they already have in that condition itself the fact that it's going to be some sort of massless boson plane. Okay, so okay, now you might say that since we can't write down an action of any kind, how do we even know that this theory is a legit theory? How do I even know that it's going to lead to something interesting? And so let's stay with our simple example for the time being. So D equals to 1 plus 1 chiral bosons. And I think it's quite instructive to see that this theory itself is something that all of you are already familiar with. It's just in a disguised way. So let's say that. So the claim is essentially that this chiral bosons, Z equal to 1 plus 1 chiral bosons, are secretly an abelian Chern-Simons theory. Okay. So let's see that. So Chern-Simons theory, I'm going to put it on a manifold which has definitely one time direction and two spatial direction that I'm going to call x and y. These are all standard Cartesian coordinates, except for one catch that now this y coordinate doesn't extend to the full range. There's a boundary at y equals to 0. So just if I draw the xy plane, it looks something like this. So the Chern-Simons theory lives below the x-axis, the y equals to 0 line. Above that, there is nothing. Like imagine that I didn't even draw it. So that's my space, and then of course there is a time which is going from all the. This is not a very physical example, but it's the simplest one which you can go to chiral bosons. But whatever I'm going to say, it works for any Chern-Simons which has a boundary of some kind. So the more physical examples are the one where you put it on disk, for example.
So the bulk was x less than 0, or was it y less than
Y.
y?
So lower half plane. And this is y equals to 0. So y less than 0 is good, y greater than 0 is the boundary. There's a bound. This boundary is included. Okay, this is there. Yeah. Okay. So the Chern-Simons action, I am sure everyone knows. There's some standard normalization and it's just simple abelian Chern-Simons, the simplest thing that you can have, right? Now, if you vary this Chern-Simons action, you get typically the one that you're after, because you want to impose the equation of motion, which is just the flat connection, the area of A equals to 0. But you actually do that at the cost of picking up a boundary term. We usually don't worry about that because Chern-Simons is either put on a compact manifold, or if it's non-compact, there is no boundary, then the usual boundary conditions takes care of that. But in this case, there is a boundary. The bulk, which is just at the flat connection condition, then we have to impose some boundary condition. If we don't impose boundary condition, we are not going to recover the bulk equation of motion. Is this point clear? Right. Now, let's just break this into component a bit for the space-time that we have. So this manipulation is quite generic. It's just taking the variation and doing some integration by parts. But now let's come back to the manifold that I'm interested in. And this one basically becomes and all of this is at the boundary, which is at y equals to 0. And the integration is of course with dt and dx only. Okay, so now it should be very clear that what kind of boundary conditions you should impose. So you can impose the boundary condition that AT is identically 0 at the boundary. You can alternatively impose AX is identically 0 at the boundary. Or you can say that, why don't I include something general, which is a linear combination of these two boundary conditions. So I can have AT minus some constant AX vanishes at the boundary. B is some constants. Some real number. Yeah. With these boundary conditions, it allows us to forget about the boundary term, which is the typical analysis that you do when you have classical field theory with on a manifold with boundary. You need to impose boundary conditions to make the variational problem well defined. And then you recover the standard equation of motion in the bulk, which is just A is a flat condition. Right? For a reason that is going to become apparent very soon, I'm going to choose B equals to 1. But you don't have to. Okay.
But there is probably just the scaling of the channels. Oh, okay.
No,
Yeah.
the scaling, I got rid of the one constant in front of one of the A's. But the other one is quite arbitrary.
Right.
Okay, so I mean, just to give away the sort of punchline, if you don't choose this to be 1, this theory is going to give rise to a theory on the boundary, which is not going to be Lorentz invariant on the boundary. So if you demand that the boundary theory is also Lorentz invariant, then this is plus or minus 1 are the only two choices you have.
Yeah, okay, yeah, you're basically redefining the right.
Exactly. Yeah. So that there is a light cone structure, consistent light cone structure on the boundary as well. Which you don't have to. Remember that the bulk theory is completely topological, right? It has way more than Lorentz invariant. It has the full diffeomorphism. And there is no reason why the boundary theory should have just one particular special subclass of it, Lorentz invariant. Yeah. In fact, this is something that condensed matter physicists do often. And they would not set B equals to plus or minus 1. For them, it might be some other number. So then, for them, it's usually called age modes, and age modes might have some velocity which is different than the speed of light. Okay. Okay, so we have found our boundary condition, and our boundary condition from now on is going to be AT minus AX equals to 0. So let's correct this upstairs, that I'm going to impose the boundary condition. Smash. But now we have a new issue, in the sense that some of you might remember already that under a gauge transformation, so let's say some lambda, the Chern-Simons action is invariant only up to a boundary point. So I'm skipping a couple of steps here, but I'm sure this is too boring to carry it out. Just do a gauge transformation. So this is anyway true for arbitrary variation, right? In specific case, when it's a gauge variation, this one is identical to 0. Right? The a being d lambda is it's a total derivative. And then the other one, I just integrated by parts so that the derivative is shifted from lambda to the gauge fields. That's the only thing that has been done there. Right? So this delta A's would be d of lambda, del lambda here. Just look at this expression that I've already told you that the boundary term evaluated, it becomes like this. And each of them, I am just integrated by parts and put the derivative of the a's and make the lambda free. And the reason I could do that is the only two directions I have left here are the t and the x, where doing integration by parts is not a problem. There are no boundaries in it. It's either time or the non-compact direction x's, where I have the usual fall-off condition at far x minus infinity plus infinity. So we have this result, which is not surprising, it's something that is known, that the Chern-Simons action is not actually gauge invariant, it's actually gauge invariant up to a total derivative term. It's a derivative, it's a boundary term. In presence of boundary, that means that gauge invariance, the issue of gauge invariance of Chern-Simons becomes a slightly subtle issue. Now, one way to deal at this point is by saying that we don't allow any gauge parameter lambda, but we allow gauge parameter only those gauge parameter lambdas which completely vanish at the boundary. Because if we have that, then this thing is all at boundary. Doesn't matter what this guy is doing, this guy is identically zero. The action is getting invariant. That's a valid solution to this problem. But the moment you choose this solution, which you have to because otherwise your gauge invariance is in trouble, then the whole theory is inconsistent. It means that the class of gauge transformations that was allowed is now being restricted. You are now allowing a smaller class of gauge transformations, which means that there are going to be certain modes which were pure gauge before that are now going to become dynamical. This is a very important point. It's a very simple statement, but it's a very conceptually important point. So if something's not clear, please feel free to interrupt and ask. So I'm just saying that if you didn't have a boundary and this, or if it was compact, or like completely non-compact, then this guy was not there. This was completely gauge invariant, and you had full. So the only restriction you put on lambda is that it's a nice smooth function whose derivative can be taken. That's it. That's the only thing you would impose.
But you had imposed the condition of A. Right?
Yeah. That's
So I guess that would also give condition of what lambda you would have, because
yes.
else you would get to an A you were not allowed.
Yes, of course. I mean, this one I was prefacing by saying that imagine that you don't have a boundary or of anything, then this would have been perfectly gauge invariant, and in fact, even this would not be required. The whole story is consistent. Now we have a boundary. Automatically, it means that we need to put a boundary condition on A. And the same reason why we need to put a boundary condition A also translates to the gauge transformations of the action, which tells us that we need to restrict the allowed set of gauge transformations. And you need to choose a gauge transformation parameter, or you need to reduce the allowed set in such a way that solves this problem. That's one. The second is that, as Klaus was pointing out, that it has to respect the boundary condition that we've already adopted. And of course, this one does. You can check for yourself, right? You can just simply take a delta. This is proportional to lambda. If lambda vanishes at boundary, that also vanishes at boundary, right? But now I'm saying that since you have restricted the total set of gauge transformation parameter that was allowed originally, and you have only reduced it at the boundary, not in the bulk. You have not restricted lambda to be anything in the bulk. In the bulk, it is still completely free to be anything it likes. Only in the boundary, if you had asked it to be exactly zero. Which means that there are going to be some pure gauge modes, which were not, so those are the modes corresponding to lambdas which did not vanish at the boundaries. They are not going to be pure gauge anymore once they reach boundary. In the bulk, they are still pure gauge. But in the boundary, they will start having dynamics because they are not part of the gauge transformation parameter anymore. So a quantum field theory, which is topological, it's just vanilla abelian Chern-Simons theory, not supposed to have any dynamics, actually can give rise to dynamics on the boundary if you put it on a manifold on the boundary. And my claim is going to be, or what we are going to see now, is that this dynamical theory on the boundary is going to be a chiral boson. And that's also going to lead us to an action for the chiral boson. Not a nice one, but an action on this. Right? Is this point clear? Okay. Okay, so the computation that we are going to do now is just a few lines, and it's very simple. We are just simply going to look into the Chern-Simons action with this boundary condition and this restriction on the gauge parameters. But we are only going to focus on pure gauge modes, because that's the only thing which can become dynamical at the boundary. Right? So let's just focus on that. And it turns out that this computation is going to speed up a lot faster if we just do a small change of coordinate first. So we are going to come back to our original coordinates at the end, but we are going to keep the t and the y coordinates the same, but we are going to make a new x coordinate, which is one of the like contradictions. And the effect this coordinate has on the components of the gauge field is that t prime becomes this, and the x prime y prime coordinates are unchanged. It's just a simple transformation that you can check for yourself, just 2 seconds. Okay. The advantage is that in this new coordinate system, my boundary condition is just a t prime and y prime equals to 0. Notice that since we have not touched y at all, the boundary is still y prime equals to 0 is the boundary now, because we have not done anything to the y actually, which is the direction which has a boundary. And if we are going to look into dynamics of pure gauge modes, we have to proceed first by fixing a gauge. Because if we don't fix a gauge, then what do I mean by, which modes are pure gauge? How do I identify? And the gauge choice, which is extremely natural for this, is simply given by taking the boundary condition and then just promoting it into the bulk. This is the boundary condition at the boundary, but now this becomes a gauge fixing condition at the bulk. So it's my gauge choice. Okay. With these coordinate system and this gauge choice, the Chern-Simons action drastically simplifies. So I have primes now. Just this two. The term involving AT prime has dropped out because AT is here. So you can have delta prime hitting on y or x, and then of course antisymmetry because there was a weight product. So all I have done is that I've just written the Chern-Simons action in this coordinate system for these gauges. That's all I've done so far. Now we are interested not in the full Chern-Simons, but we are interested in those modes which are pure gauge modes. For these gauge choice, the only pure gauge modes that can appear are Ax prime equals to del x prime of some lambda and A y prime. Right? There is nothing for us to do at AT prime because we have gauge fixed it to 0. So some lambda has been already chosen which forces AT prime to become 0. And in that choice, the only pure gauge modes that can appear is one which makes Ax prime and Ay prime, del x primes and del y primes of that same function. So now all we want to do is that substitute this on this. And that's going to give rise to an effective action for the lambdas. Yeah, everyone's on it. Okay. So I should go up, right? First, it should just- Wait, what happened?
It's at
Sorry.
your eraser is in the bottom bar.
Oh, okay. That's a good. And I should push it. Is it visible?
Yeah.
Yeah. Okay. So as I said, now all you need to do is that substitute those things back, and then maybe I should just let it below that. And a little bit of juggling will show you that you get two terms.
Oh, so what was the logic about that? I mean, so we had a gate, we first took away the gate symmetry by imposing the gate symmetry T minus 0 in the bulk. And but this looks like a pure gauge.
Yes. So the logic is that what is pure gauge in the bulk would become dynamical in the boundary.
Oh, okay. That's what we are looking for.
Yeah.
We're
So
looking for that.
yeah. So I argued that already, and that's why now I want to derive an action for those pure gauge mode at the boundary. And to do that, all I'm doing is that in the Chern-Simons action, I'm just looking for the Chern-Simons action. I'm just looking for the dynamics of just the pure gauge mode, and then seeing what I get. If my argument is correct, then I should be able to derive an effective boundary action, which is dynamical, without any further input.
Right. So you're not claiming that it's the full Chern-Simons theory, but it's like we have now restricted to the pure gauge.
Yes.
Kind of.
Yeah, absolutely. Because if it is not pure gauge, then I have no argument to tell you that why that should become dynamical at the boundary. But pure gauge modes, I can, because I have restricted the set of gauge transformations. So there are bound to be some pure gauge modes which will become dynamical at the boundary. And I'm just trying to derive it without any additional input of any kind. And this is reasonably straightforward algebra. You just add, subtract like terms and stuff like that. And we see that we have two total derivatives, one with respect to y prime, one with respect to x prime. And then once again, let me remind you that we have not done anything to the y coordinates. So boundary is still at y coordinates. So this derivative, when we integrate by parts, is actually going to vanish, because at the boundary of x's, we are going to impose the standard form of conditions. So this total derivative we can forget about. But this one is just going to get rid of this y integral and make me give an answer of this evaluated at the boundary. This gives rise to the effective theory, which is this. And now I can go back to my original x's. The whole purpose of going to x prime and t prime is that so that I can go from that to this in as few steps. If you don't do that, you can still derive this. You just have to go through maybe a few pages of calculation. That's the only difference. Now, if we go back to our original coordinates, just by inverting those ones written upstairs, you have what might look familiar to some of you. And mind you, this is all at y equals to 0. So this is not just any dx plane, but the one which is at y equals to 0. Because I have integrated, I have obtained this by integrating.
Yes, I think I've seen this in Jackie,
Florian.
Yeah.
So this Lagrangian was written down in late 80s. Florian for a candidate Lagrangian or action for a chiral boson. Why am I calling this a chiral boson? Well, let's quickly look at its equation of motion. So if this is a new action, forget about this normalization, it's just there. So you have the equation of motion is del T of del x lambda minus del x square lambda equals to 0. This doesn't look like the equation of motion of chiral boson that I have now erased, but was there some time ago. But if you define phi as del x lambda, then you see this one is semi del T phi minus del x to be 0 or del minus. So what we have shown here is that free chiral boson is actually the boundary dynamics of a abelian Chern-Simons theory defined on a manifold with a boundary. The boundary is precisely where the chiral boson lives. And by the way, I should also point out that if you had not said that v equals to 1, you would have had like a v hanging around here. And that would have signified a chiral wave which is propagating with speed v and not speed of light. So it is of interest if you're interested in non-relativistic physics. But if you had wanted this Lagrangian to be Lorentz invariant, well, okay, the action or the equation of motion to be Lorentz invariant, then v plus minus 1 is the natural choice. Yeah.
So in Chern-Simons, that k is the level of the area it has some. Does it have any significance here?
It doesn't have any significance if you want to think of the boundary theory on its own.
Okay.
But if you want to remember that it's this, because this is the simplest, but also this is the most rigorous description of holography that you will ever see. Because we started with the bulk and we derived the boundary. So if you want to have an interpretation in that sense, then you have to remember that okay, there was a constant sitting in front of it, which was level quantize and stuff like that. But just the boundary theory by itself doesn't know about this.
Okay.
It might be a stupid question, but it seems that since we have put a very sharp cutoff on the boundary, also for our gauge fields, that they should just die down on the boundary. If I'm careful and choose my gauge transformations as something which slowly dies down on the boundary, will they still have dynamic effect on the?
It's not really sharp cutoff in the sense that when I say that lambda has to be 0, I did not say anything about how any condition about the derivative of the lambda. Right? It's just a boundary condition, simple boundary condition. Of course, I want the derivative of lambda to be everywhere well defined within the bulk. That in fact tells me that it cannot be something which drops off to 0 like this on the boundary. It cannot. Because then in the bulk there would be a singularity. And I don't want that. So of course there is a smoothness condition inherent in all these boundary conditions. This is not really any sharp cutoff condition. It's really a simple boundary condition. I have a boundary, and boundary, well, by definition, boundaries are abrupt. There are no smooth boundaries, so to speak. It just ends somewhere. Right? So okay, couple of things about this Lagrangian is that first and foremost, the dynamics is Lorentz invariant. Does the action look Lorentz invariant to you? It looks weird, right? The Lorentz transformation property is completely implicit, it's not manifest of any kind. The second weird property is that what appears in the action as a dynamical variable is lambda. When we derived this equation of motion, we varied lambda. But that did not give us chiral boson. We had to do one further identification, which was the spatial derivative of lambda to be the one that we are interested in. Which means that if this guy is really transforming like a scalar, albeit a chiral scalar, but still a scalar nonetheless, this guy is some sort of a non-local combination of the scalar. It's not a nicely transforming field by itself. So you have this thing that you could somehow guess a Lagrangian, but that Lagrangian has all sorts of problems. And this is, remember, this is still free theory. We haven't even started putting down interactions. So if I am to do any computation with it, I'm going to be in all sorts of problems. The fields are not nice ones. They have weird transformation property. The symmetry which guides me in doing computations and doing consistency checks is not manifest. Right? So in some sense, we have an action, but it's not a consistent one. At this point, you or anyone could have said that, okay, fine, an action or a Lagrangian seems to be a tall ask, but could we have described all of this in terms of a Hamiltonian? You might have said that, okay, I give up trying to write down a Lagrangian, but Hamiltonian is the next best thing. I might not have manifest Lorentz symmetry, but it's still not that bad. We know how Hamiltonians transform, and it's not a bad transformation at all, right? Well, it turns out you can. So the Hamiltonian for this would look like this, but this phi is meant to satisfy the bracket, which looks like this.
Oh, you mean, so by Hamiltonian, you mean we give up an action principle, but we just want to see if we can get Hamiltonian equation?
Exactly. Can we get a Hamiltonian equation of motion, which is this?
But I mean, my viewpoint is that Hamiltonian Lagrangian are actually, more or less speaking, equivalent, and you can of course have a Hamiltonian action principle.
Yeah. I mean, my point is that the Lagrangian clearly looks ugly, but maybe the Hamiltonian is better.
Well, I mean,
I agree. I completely agree, and that's just the point that I'm going to try to make. So you write down a Hamiltonian which looks much simpler, but then you have to impose this bracket, right? The point. This is not strictly speaking Poisson bracket, but whatever is the correct bracket in this phase space. Right?
well, it's not canonical for some bracket, but it is a Poisson.
It is a Poisson bracket, but it's not the canonical Poisson bracket. That's the correct thing, and it's equal time. Okay, I'm suppressing the time coordinates, but I think that these are always equal time. And you have to impose this, and then with this you can easily show that if you want to evaluate phi dot as your Hamilton's equation of motion, then you get this. And it's just 2 lines of, not even 2 lines, only 1 line. Now, you might say that Hamiltonian is written in terms of phi, which is the variable of the chiral boson. The Lagrangian is written in terms of lambda. Why can't I just simply start with this, do a Legendre transform, and get to a Lagrangian in terms of phi? Maybe that will look nice. The whole problem was using lambda instead of phi. Well, you can do that, and Subhroneel and Jakib, in fact, did do that. That's the Lagrangian they had in their paper first, and this one rather came second. And the Lagrangian looks like this. It's not local anymore. That's the price you have to pay. You can choose to work with a local nicely transforming field, which is actually a scalar. Lagrangian becomes non-local. Or you can do a redefinition. Do a redefinition like this, which is non-local. But in terms of this lambda, you get back that local Lagrange. So you have a very pathological, exceptional, ugly situation, even just for a free field theory. And all of this I am elaborating with the example of the two-dimensional chiral bosons, but all of them has an analogous story in higher dimension, including the Chern-Simons story. The free self-dual form fields can always be thought of as bulk of. So all of you probably know that the abelian Chern-Simons can be written in any 4k plus 3. And it's not a coincidence that the 4k plus 3 is the one where you have abelian Chern-Simons, and then 4k plus 2 is the one where you have self-dual and self-dual. And of course, this story of having interesting boundary dynamics of Chern-Simons on a boundary this is perhaps the simplest one. The most interesting one is the one where you have non-abelian Chern-Simons and you have residue orbital models in the boundaries. But just to emphasize that the simplest cases are also sometimes rich enough. Okay. So I hope I have convinced you that even though this looks pathological, as a field theory, even the free field theory, it exists. Because I can always define it holographically using a Chern-Simons theory in the bulk. Right? But of course, that's not all. We know many other places where self-dual fields naturally appear. So I think all of you know the standard examples. So easily the best and the most famous example is type 2D string theory. It has a self-dual Raman 5-form flux. And because type 2D string theory has that, any moment you compactify it on a K3 or a T4 to get a 6D supergravity, typically you will always get a chiral tensor multiplet. Which has a self-dual 3-form flux. So this is an example in 10D, which is 4 into 2 plus 2. This is an example in 6D. Another interesting example in D equals to 6 is wall volume theory of M5 grids. So there is a everyone knows M5 grids, right? Okay. So and D equals to 2, you already saw one example. One other interesting example that I can tell you about is the Walsh theory of heterotic strings. Heterotic strings, right? They have one sector which moves in only 10 dimensions, and there is one sector which moves in 10, but then there is additional 16 internal dimensions. So you need to have some sort of chiral bosons. You cannot have simple bosons because they will end up propagating in both sides. So if you want to create an asymmetry between the left and the right sector, which is what heterotic string does need to do, then you need to write down an action involving chiral bosons, the Walsh reaction. So these are just some of the examples And as you can see that all of them are very intimately connected to string theory. All of them are examples, even if you want to think of this as some sort of gravity theory or etc. These are all something which are nicely sitting within the full string framework. So there is no avoiding several form fields or several fluxes. Okay, so just to sort of, I'm not going to give you the full history of this, but just to sort of give you some pointers. That typically attempts to describe these form fields in generic dimensions has been of the following classes. One is something akin to Florin image active. That is, you have something with non-manifest Lorentz symmetry. Which means it's hard to do computations with, but nonetheless you can. If you persist and you're stubborn enough, you can do something with it. So just like we did today. But it's definitely a painful way. I mean, just for free field theory, we have to do a lot of work. The second one is that you do have manifest Lorentz symmetry. They come at one of the two costs. One is that you need to introduce Lagrange multiplier or auxiliary fields, but an infinite number of them. And the second one, which is kind of like an improvement of the first one itself, has finite number of auxiliary fields. But the action is non-polynomial. What do I mean by non-polynomial? I mean that in the Lagrangian there are terms where you find sitting in the denominator with something up there, this kind of nonlinearity. What's the problem with this approach? If you work with infinite number of auxiliary fields, and by the way, if you have infinite number of auxiliary fields, the action is polynomial, normal, like the ones we are used to. But the problem is that if I want to do quantum theory with it,
and by polynomial, you really mean polynomial, not power series.
I don't remember this, so I'm not going to commit to an answer for this one. But what I'm going to say is going to be true for either way. So then the point is that, in fact, it is polynomial. It's not power series. Yeah, it is polynomial. So the problem with this is that if I want to do quantum theory with it, right? So you can integrate out these auxiliary fields. In principle, you can solve all of them, plug them back and do it, but in practice, you have to solve an infinite number of equations. So you're never going to be able to do it. It's something, it's good to write down in classical, but you can't do any quantum computations with it. This one is even worse. I don't even know how to go up quantization starting from this. Now there has been a lot of work. So this one actually goes by the name past disorderly and atomic formalism. By far the most famous formalism in chiral bosons. This one has a lot of successes, and there has been a lot of work which has shown that in principle you can carry out a Dirac constant quantization for these theories. But I want to emphasize it's in principle, like for actually genuinely interacting theories that we have in our hand. I don't know of a single example where people have actually done this quantization and consistently carried out the computation. So it's one thing by saying that, okay, in principle I can do it. It's another thing that actually doing the computation. Okay, the third kind, this is something that usually not mentioned in the papers, but I like to mention it, is what I call textbook. By now there are tens of textbooks on string theory and supergravity, right? All of you have your favorite ones. And all of these examples should appear somewhere in the textbook. So what do they do? right? So type 2 supergravity, for example, for sure would appear there. Well, what they do is very simple. They said that you take the Lagrangian to be f with star f, but do not impose f equals to star f at the level of Lagrangian. You derive the equation of motion first. And on the equation of motion, you impose f equals to star f. So this is what is called a pseudo action, because it's not really the action, because you're kind of relaxing the condition that you are actually after. So you're allowing for more degrees of freedom, so to speak. But
Pseudo action.
Pseudo action.
Zero.
And this thing is fantastic if you want to work with the equation of motion, because it's very easy to derive the equation of motion, just a standard calculation. And then on the space of solutions of the equation of motion, you can just simply replace f equals to star f. And at this point, a curious student would start asking that, oh, but how do I do quantum computations with it? Because this action is well suited for classical analysis, but it's not well defined for quantum mechanics. I mean, quantum mechanically, it is describing completely something else than what you want. And at this point, the textbooks quickly point out that look how many interesting solutions type 2 supergravity have classically, and then describe it. Right. So that's the third one. And the approach that is our highlight, sense formula. And what I'm going to elaborate is that this is going to be manifestly Lorentz invariant. This is going to be polynomial, and therefore straightforwardly quantizable, and you can actually perform explicit quantum computations with it. Okay, I'm probably doing very poorly on time, but
Do you have some more to continue? Or to stop here?
oh, I have plenty more to continue. But the core question is that you have enough energy to. No, okay, not plenty more. I guess if you give me 15 minutes or so, I can reach a point which is a nice stopping point, and then we can pick up.
Yeah, it's okay.
We have time to 3:30 here, so.
Okay. Okay, so if everything is so nice about sense formalism, then how come it was not discovered earlier? And the reason for that is that while these are the pros of the formalism, there are some cons. And these cons, I will put it on within quotes, is that this formalism has several unusual features. Once again, unusual within quotes. And the reason within quotes is that these are unusual from a field QFT perspective. Like if you are asked to do a quantum field theory of self-polar and self-polar field strengths, the way you would approach is kind of in synergy with all other field theories that you have learned so far. So they are unusual from this perspective. But I'm going to explain to you that they are actually quite natural or more to be expected from a string theory perspective. So that's why I put unusual within the quotes. And we are not going to cover all the unusual features in one lecture, so don't worry. We're going to uncover them one by one systematically. But there are going to be certain features which are going to make you like, I mean, why are we doing this? But there are justifications. Okay. Okay, so the first unusual feature that I want to emphasize is, okay, it's kind of like, let me summarize it with a slogan. It's doing gauge theory without gauge fields. What do I mean by that? What I mean by that is that sense formalism, we are going to work with a field which satisfies the self-duality condition. But we are not going to think of F as a field strength of some gauge potential. We are going to take the F itself as a dynamical variable and not C. So in sense formalism, we are positing that the field strength like variable itself is a dynamical variable. The field strength is not to be thought of as a field strength. It's not to be thought of as a curvature of a potential. This is a very, very weird claim. If you take Maxwell Lagrangian, and you claim that F is your dynamical field, you get equation which is F equals to 0. So the moment you change what is your dynamical field, because in your action this is very important. Whenever you define a Lagrangian action, you have to basically tell me what is the phase space, what is the configuration space, right? What is the space of fields over which this Lagrangian action is defined. And if I change that definition itself, I say that the field strength itself is the dynamical field, and I am not going to think of it like a fundamental, like a field strength. Yeah.
Then it's not a field strength, right? Then
Yeah. Then it's not a field strength, but then what is it? I mean, for the lack of a better term, we keep on calling it a field strength in a sense. Another justification might be that in the free cases, on the space of solutions, you can always re-express them in terms of some gauge potential. But it's the real difference is going to make is in offshell. It's going to actually allow us to write down an action, which we couldn't in terms of this. Now, so this is, everyone agrees that this is an unusual statement, or this is an unusual assumption to make from a QFT perspective, right? For an abelian preform theory, right? Before I justify that why this is to be expected from the string theory side, let me just point you out one thing, is that this is actually a good assumption to make, or a sensible assumption to make in case of this self-dual condition. Why? Because if you had actually taken F to be some DC, you see what we were calling the dynamical equation implied by the self-duality, like D star is equals to 0. This is actually secretly nothing but the Bianchi identity. Because of the self-duality condition. So the dynamical equation is actually not really that dynamical. It's secretly just an identity. It's an identity mapped to a dynamical equation by this concept. But you see, this is only an identity if you think of this as a field, as a curvature of a potential. If you don't do that, if you think of it just as an F, then your equation is simply, if you have an equation which is d of f equals to 0, which is the same as d star f equals to 0 by the condition, and you don't think of f as some DC, then this is fine. This is a perfect fine. It's some first order equation of some variable f. We will see how to solve it or how to make sense of it, how to do quantum theory with it, blah blah blah. In itself, there is no problem with this. Okay. Okay, so why do we expect this from string theory side? So
you forgot the
that's the point.
But why did we get df equal to 0 if it's not an H field?
I mean, I'm saying that if I get an equation of motion of that form,
But
if I get,
yeah, well, oh right. So but you have given no clue where that would
Yeah,
come from because
yeah.
you don't have any ubiquitous.
yeah, exactly. But I'm yet to write down a Lagrangian. So I'm saying that if there is a Lagrangian which gives me that equation of motion, that's perfectly fine. I don't need to think of it like an identity being mapped to something that looks like a dynamical equation. Okay, so why the string theory says that this is a natural thing to do is that, remember, the quintessential example in string theory is the Raman-Raman 5-form flux in type 2B. But in fact, all the Raman-Raman sector in type 2B and type 2A has a very simple property that if you think in terms of, so okay, there is a textbook construction of the supergravity action in string theory, where you actually don't take much input from string theory except for its massless spectrum. You look at what is the massless spectrum, you look at the amount of supersymmetry that string theory has, which is the maximal amount in these cases. And then you just sort of reverse engineer and say that, okay, I mean, this is the unique action kind of you can write down in 10D with this amount of supersymmetry and these massless fields present, right? Supersymmetry kind of fixes everything for you, so to speak. So that's one way, but that's not a very stringy way of deriving it, right? It's kind of reverse engineering. A stringy way of deriving it would be that you look at the scattering of strings. Say 4-point scattering, 5-point scattering, so on and so forth. And just look at classical scattering, because you're worrying about the classical action, right? Look at this string, classical string amplitudes. You know how to compute them from the wall shape. Look at the answer, and then try to see that what action with, and you can take a, if you want to be even more precise, you can take a point particle limit. This becomes some field theory diagrams. And then you try to say that what field theory Lagrangian gives rise to these Feynman diagrams. That's one way of deriving the space-time action for type 2 supergravity. Now, if you do that, you are going to see one thing is that if you want to just focus on the Raman-Raman sector or the scattering of the Raman-Raman external states, this computation. So, how many of you are familiar with doing a wall sheet computation? Yes, no, maybe 5%, 10%. 5%. I shouldn't have given those. Okay, so all of you know that to evaluate this, you need to compute some correlation function of something called vertex operators, right? And you need to construct the vertex operators for the states which you are trying to scatter. In the Raman-Raman sector, the vertex operator is a boson by virtue of it being a bispinner, because each Raman sector is essentially has an oscillator rotation annulation mode which has a space-time spinor index. It's basically secretly a bispin, which we convert to a sort of space-time index of the Lorentz index in a standard way by finding appropriate products of gamma matrices. And these gamma matrices are going to have some indices, Lorentz indices, right? If you're in type 2B theory, that means that both of your spinor indices are going to be on the either lower or upper, whatever is your convention typically is lower, right? And the correspondingly, the products of gamma matrices, which also has both to the upper, are the ones which has odd number of gamma. So it can be a single gamma matrix, it can be product of 3, it can be 5, and in principle you can also have 7 and 9. But in 10 dimensions, the 7 one is actually the 3 one, the 9 is basically the 1, and the 5 is the 2. This is just a property of representations of free model. And with this new Lorentz indices that you are going to have here, you are going to have some polarizations which are going to need to contract with that. So what is going to appear here is some fields with either 1 or 3 of 5 indices. And you already know that this one has to be self-dual because this gamma matrix is self-dual. Right? And even without doing the full quantization, just based on group theory and little input from string theory, you could have already guessed that what appears in the spectrum of type 2b has to be some 1 form, some 3 form, and the 5 form. And you see what appears in the fluxes directly are the field strengths. Now you might say that, well, how do you know that this is a field strength? Why can't I think of it like, you know, del of A or some del of CM, MN, and so on and so forth? That's because I can, when I compute this correlation function, it's these guys that are going to have contraction. It is these guys that are going to give me propagators. In the vertex, it is these guys that are going to settle. So in the field theory limit, it's going to give rise to a Feynman diagram where the propagator is between two f's. So if you really do an honest string computation and take its point particle limit and try to figure out what action it comes from, you would actually find that what is really the dynamical variable is the field strength. And this is true for all Raman field, by the way, not just the self-dual. And a similar argument holds for type 2a, except that you need 1 up, 1 down, so those are the even ones. That's why you have 2, 4, 6 in type 2a. And in fact, funnily enough, even before the advent of full RNS formalism for strings in 1881, Witten and Alvarez-Brown had a very seminal paper on computing gravitational anomalies. And they were computing, so there is a very famous result that if you have a chiral theory on flat space and you try to couple it to curved space backgrounds, so typically they will give rise to gravitational anomaly. So they were looking at all the cases. So you have left-handed fermions, right-handed fermions, and so on. In the bosons, the interesting case is what? Self-dual things. So they wanted to compute gravitational anomaly for self-dual form fields as well. But they didn't have an action. So how do you compute them? What they did is that they had a very famous line, at least famous to my mind, because I find it very ingenious. They said that let's be pragmatic and let's just invent a Feynman. Let's not derive it because we can't derive it. We don't have an action. Let's just invent it. And the way they invented it is that they said that I'm going to define the propagator in terms of f and f. So it's going to have, you know, k by k squared, and then of course other indices and symmetrization. So this is the propagator for the field strength. If you had propagator for gauge fields, you would have just had 1 over k squared and then the things. The fact that you had 2 k is on the numerator, but the fact that this is like, you know, degree same as numerator and denominator is reflecting that this is really a propagator of the field strengths. And then for the vertex, they said that let's look at the stress tensor. Let's compute the stress tensor for the simple standard Lagrangian that we would write down for the pseudo action. Compute the stress tensor, and then on that stress tensor impose that it's self-dual. And let's couple the graviton to this stress tensor. And these are the Feynman rules they invented. They couldn't derive it. There was no action. They just simply said that, okay, this seems like a sensible thing to do. Pretty much the only thing we can think of. So let's assume that and let's compute the gravitational anomaly. Gravitational anomaly computation means that you, in 10 dimension, it means that you have to compute a one loop diagram, which is the hexagon. And these are all gravitons. And these solid lines are the F lines, right? And the vertices are governed by the simple minimal coupling, the stress tensor coupled to this H, and the propagators are given by this. So they just computed this one loop diagram. And there are some arguments which tells you that why this is one loop exact. You don't have any further corrections for 2 loops and etc. Let's not get into that. But this is an exact result. There is some answer they computed. Why is that a big deal? The big deal is because there is something in type 2b spectrum. You have a lot of theories, a lot of particles which have chirality. You have, of course, the self-dual thing, which has a chirality, but you also have the superpartner of the graviton-gravitino, which is, say, right-handed, and the superpartner of the dilaton, which is dilatino, which is left-handed. So in the type 2b, you have a right-handed gravitino, you have a left-handed, so this is some spin free of particle, you have a left-handed dilatino, this is some spin half particle, and then you have a self-dual type form. And all of these are sources of gravitational anomalies because all of them individually violate chirality. And when you couple it to gravity, they can give rise to gravitational anomaly, which means that diffeomorphism or general coordinate invariance is not a good symmetry of type 2b. And it would imply that type 2b is an inconsistent theory. And this was a big deal in mid-80s. Unless something happens where the way this violates the anomaly, and so the way where this creates the anomaly, where this creates the anomaly, and where this creates the anomaly, somehow magically all cancel out each other. Now, computing this and this is non-controversial because we know what are the actions for formulas. They are very standard. You can compute similar bond-loop diagrams. You know the answer. This one, when you use the Feynman rules that were suggested by Witten and Albers, shows that they exactly cancel each other, giving rise to a consistent type 2b theory. And of course, we have independent arguments that why type 2b is a consistent theory. So this also tells us that this weird Feynman rules that they somehow guessed, they somehow invented, has to be the correct one. It's just that we don't know what action will come from. So even though it seems like working with field strength is counterintuitive, it's not something we should do. That's what we should do. Okay? And then just to close, we want to have a field strength like this. So let's look at the simplest example for Sen's formalism, just free chiral bosons in 4n+2 dimensions. How do I do that? As Klaus pointed out, that how am I even going to get an equation like d of f equals to 0? Even if I think of f as a fundamental thing, because there are no derivatives. If I can't think of f as having a derivative of something. So the solution is quite clear. If you write down Lagrangian solely in terms of f, you can't do that. So you have to introduce something extra. So the Sen's action, just the free case. So this is just the Sen theory free flat space type. Simplest thing you can write down. So what are these objects? So P is a 2n form. Remember we are in 4n+2 dimensions, and 2n+1 has to have the self-dual condition. So this Q is the 2n+1 self-dual field strength, which means that even by definition, it satisfies that Q equals to star Q, even off shell is by definition. Sorry, not Q. I wrote, okay, maybe I think Ashoke calls it Q, so let me put Q here. So Q is the one we are after. Q is the degree of freedom we are after. But we have introduced an additional field, which is some 2n form, which is called a P. And not only that, we have given it dynamics. It's not auxiliary anymore. It has a kinetic term. So it seems like a crazy thing to do. We have considerably enlarged our theory space. Like whatever is the degree of freedom, we have enlarged it. But why does it work? Well, let's look at the equation of motion of this very quickly. So if I vary with respect to p, and if I vary with respect to q, is this clear that y if I vary with q is dp minus star dp? It has to do with the fact that this is by definition self-dual. So I can decompose it into a self-dual and an anti-self-dual part. The self-dual part is identically zero. So when I vary q, it's only the anti-self-dual part which has to be set equal to zero. And the anti-self-dual part of dp is dp minus star dp. The variation of this one is, there is nothing. You just need to take the d on that side and stuff like that. Now, how does this help us? Look at this second equation. Take another d. Because if this is 0, d of this is also 0. You can get rid of this and you get d star dp equals to 0. But if d star dp is equal to 0, this equation means dq equals to 0. So even if I have introduced an extra field, and in the Lagrangian they seem to talk to each other, I can show that at the level of equation of motion, they completely decouple. Therefore, we can just simply focus on dynamics of this without worrying about what is happening here. You can evolve this whole theory using the whole Hamiltonian, you can do full computations, but it will always be nicely factored out. And you can just focus on the physical field that you want and forget about this extra, what is called an unphysical field, but it's not an auxiliary field, it's a dynamical field. It's satisfying some sort of field equation. So this is the simplest version. Now, what are the things that are coming up? And with that, I will stop. This is just for free theory. Now we need to turn on interactions. And we need to ensure that we need to turn on interactions in such a way such that this continues to hold through. These extra fields dynamics must always decouple from the one that we are of interest. We have to make sure. That's first thing. The second thing is that this is at the level of equation of motion. We need to make sure that this continues to be true at the level of full quantum theory. So the next day, what we are going to do is that I'm going to introduce the interaction, and then I'm going to show you the full quantization of this with interaction present. And we will see that how, even in quantum theory, the decoupling continues to be present. And then after that, there is a non-trivial thing, is that we need to couple it to gravity. This is flat space time so far. And that is quite tricky, because this might remain completely decoupled from Q. But if you naively turn on gravity, this will start talking to Q through gravity. If you just naively take this star to this with respect to G and this integration with respect to square root of G, etc., then this couples to graviton, this couples to graviton. Q have a stress tensor, it will couple to graviton. And through graviton, T might affect Q. So you cannot turn on gravity naively. You have to turn it on in a very different way. So we will see how to couple this to gravity, and then we will look into computations, whichever one you like. There are some explicit quantum computations that you can do and stuff like that. So, by the way, I should tell you that this is the second unusual feature, that we are interested in the dynamics of Q, but we are writing a Lagrangian which involves an extra additional dynamic. So, okay, with that, I think.
Yes, is it like the H kinetic term for the 2D case in the Lagrangian?
Are you saying that if this is a pure gauge thing? No, it's not a pure gauge thing, right? It of course it has a trivial gauge invariance. Like if I shift P by B of something, then it's of course gauge invariant. But this is not a pure gauge. I'm not going to make it pure gauge. It's really going to be a genuinely dynamical field. And next week when we do the quantization, I'm going to show you that the Hamiltonian for this is not something which is trivially zero or anything. It has some Hamiltonian of P here.
If I put n equals to 0,
Mhm.
it is a scalar.
Mhm. This is a scalar. P is a scalar. That's right. And but this Q is the one form that I'm not going